You are watching this video on a computer, and it is extremely complex the way computers work, and there's a couple of different ways in which we can actually break down how a computer works down to its most basic concepts. At first, you can break it down into its parts: the GPU, the CPU, the memory, RAM. I'm no expert on the internals of a computer, but there are a lot of essential parts to a computer that most people are familiar with. But if you were to go further than that, a computer can be stripped down to a bunch of microscopic physical representations of 0 and 1. And there's actually quite a unique way that you can represent said zeros and ones. Very simple machine called a Turing machine. Thought up a long time ago, a Turing machine is a machine that has a set of rules, and it applies said rules onto an infinite strip of zeros and ones. Now, initially, all binary numbers on the strip are zeros, and the Turing machine starts with rule A. However, with every rule, it tells you whether or not, based on the number, if it's 0 or 1, it gives you an action that you need to perform. First of all, you need to change the number either to a 0 or a 1. So you're either changing it or keeping it the same. Secondly, you either move the strip left or right. There's infinite strips, so this could go on forever. The third action is that it'll send you to a new rule. And depending on these rules, you can have a 2-rule Turing function, a 3-rule Turing function, all the way up to infinite amount of rule Turing function. Now, obviously, this isn't exactly how a computer works, but it is a very simple conceptualization of a computer. If you have already heard of a Turing machine, you may already know where I'm going, and that is with the great mathematical problem of the busy beaver. I don't cover math a lot on this channel, but I have been very fascinated by the concepts of busy beavers. And I have found a plethora of amazing visuals online regarding said busy beaver. To explain the concept of a busy beaver, I have to first add a new rule to our little Turing machine. And that rule is the halt rule. So rather than sending the Turing machine to a different rule, one of the rules will refer to a halting stage, where the busy beaver stops moving and doesn't do anything else. And this brings up the really interesting question of what busy beaver, for each amount of rules, let's say start off with 2 rules, can go on, travel the most amount of steps before halting. A Turing machine is disqualified from being a busy beaver if it doesn't travel the farthest amount of steps before halting, or if it runs infinitely. And to actually calculate such a busy beaver is very difficult. And we have only calculated the busy beaver of 4 or 5 rules, because obviously the amount of busy beavers grows exponentially, and the amount of computation to determine whether or not they stop or go on infinitely is very difficult. In fact, for some busy beavers, the entire determination of whether or not they will stop is based on some very complex conjectures, because once again, this is literally a program, so it can go into any math concept. So fascinated by Turing machines and busy beavers, I wanted to create a visualizer for it. As I said earlier, there are tons of great images that visualize busy beavers and a lot of great videos explaining said busy beavers. But I wanted a program that you could input any busy beaver into, and it would give you a visual video of said busy beaver in action, or said Turing machine if it isn't a busy. So I looked for a library, and I eventually chose Manim, which is a really great library made by 3 Blue 1 Brown that allows you to visualize math and, frankly, anything. It has amazing transitions and is very quick and easy to understand. Learning Manim was a little bit difficult, but the concepts are pretty straightforward, and a couple of tutorials later, I had a basic concept of Manim. To start off with the visualizer program, I first had to come up with a way to represent a Turing machine. That wasn't too difficult. Then I figured out how to manipulate said data, under which I used 2 arrays in Python to represent the infinite strip of zeros and ones. The second, and arguably most important part, was actually visualizing this. And so I basically took the code that I had just written for the information part of this entire program, and I applied it to visuals, which gives you this really cool animation for any Turing machine. Also, a neat little feature that I added in the bottom left corner was a table showing you the rules of the Turing machine. So, to represent any Turing machine, you can input the Turing machine rules as well as a limit of how far you want the program to travel, because we wouldn't want our program running infinitely. So I did add a cap. Using this program, we can very easily represent the busy beaver of 2, the busy beaver of 3. We can also represent some other very interesting Turing machines, such as a busy beaver, which results in the most amount of 1s. Because, fun fact, for some of the lower values, there are multiple busy beavers. And when we look at these programs visualized, we can actually get a sense of a pattern. While I don't think I can actually contribute to finding the future busy beavers, I think that such a visualizer can actually give some people interested in such a subject and maybe spark an idea that can help us figure out more busy beavers. Because Turing machines and busy beavers actually has a connection to a very famous mathematical problem called P versus NP. Now, I am no mathematical genius, and I would have a very hard time explaining P versus NP off the top of my head, but what I can tell you is that it is a very important problem when it comes to a lot of things computer-like, especially with the rise of AI and the digitalization of our world. So busy beavers might actually be really important. If you are interested in such a subject, I encourage you to go watch more detailed videos on busy beavers, as I am a programmer once again. Though I do love math, I am not a mathematician, and I can't give you a sufficient overview of how Turing machines and busy beavers truly interact with the mathematical world. But without further to say, I hope you enjoyed my animations, and if this video gets 100 likes, I will post the code. So drop a like and subscribe. I'm trying to reach 100 subscribers before I finish 100 legal problems, and I am getting close. So smash that subscribe button, and also leave a comment. What do you want me to do next? I do all sorts of stuff. Watch another video, and I'll see you on the next one.